Hey, Algebra 2 students, this is our extra practice for finding zeros using factoring, and this actually belongs with lesson 11. So if you wanted some extra practice from lesson 11 in your Algebra 2 class, this will be a good place to get you started practicing some of those skills. The objective for today is to find zeros of functions and their multiplicities, and the way we're going to do that is by factoring our polynomials down to help find zeros. So there are the standards we're focused on. With this one, this sort of ties together too. We're going to be using the structure of our expressions, so what they look like, to help rewrite them. And then once we've rewritten, we'll be able to identify our zeros very easily. So that's our goal. Here's a quick refresher for these factoring tools. These are the tools we've been covering so far. And I say tools because there are a bunch of different ways we can factor. When we look at a problem that we'd like to factor, these are the things we're going to go back to and be like, does it look like a difference of squares? Well, if it does, I can apply this pattern and split it up into a minus b and a plus b. All right, maybe it looks like difference of cubes. If it does, we can split it up that way, or sum of cubes. Or if it's a quadratic, in another video, in our diamond box method video, we talked about ways we could use the diamond box method to factor our quadratic into two different pieces. So we're actually going to be using all 4 of these different methods today: difference of sums, difference of squares, difference of cubes, sum of cubes, and diamond box method to help find our factorizations and then also help us find our zeros. Okay, I'm not going to spend too much time on recapping how to use these. We'll kind of see them as we go. What we're going to focus on right now is, first of all, how we're going to find a zeros, or what it means to be a zero of a function. So here in this first line, I have an equation. There's 4 different things, a, b, c, and d, and they're all being multiplied. It could have been like little x's. They're all being multiplied together to make 0. So what's special about that is that when things are multiplied to make 0, it could be that any one of these 4 letters, a or b or c or d, any one of them could be 0. So say for example, a was 0. If a was 0, I'd put 0 for a times b times c times d equals 0. If a is 0, it doesn't matter what b, c, and d are. We're just going to be multiplying all of them by 0, so our result will be 0. So one solution for this equation would be a equals 0. But we could also do that if we put b equal to 0. B equals 0 is a solution. If I plugged a 0 in right there where b is, it would be a times 0. Oh, that's 0. And then 0 times c is 0, times d is 0. And that is equal to 0. Check. So when we have an equation equal to 0, any one of the things being multiplied together can get us can be a solution. So for this one, there are 4 possibilities. Either a, b, c, or d could be equal to 0. We can use that same logic, that same setup, to help us find the zeros of polynomials. So here's a polynomial, a function f. And if it asks us to find the zeros of f, what it means is find the values of x, so we're going to get some values of x in the end, where the overall function is equal to 0. So when it tells me to find zeros, I like to set it equal to 0 like this. And then I start to look at my terms and see what's being multiplied by what, if we can figure out what values of x would make this equal to 0. So just like above, with the a and the b and the c and the d, we have things being multiplied together here equal to 0. And just like we found out above, if they're being multiplied together to get 0, any one of them, any one of those terms could be equal to 0. So for example, this first term, x plus 2, this could be equal to 0. That's a possible solution. The second term, 3x minus 5, that could be equal to 0. So just like we did with the a's and the b's and the c's and the d's, we're just splitting up our factors of our polynomial and setting each of them equal to 0. That will give us solutions. If I went on and solved the first one, x plus 2 equals 0. If I want to solve for x, I want to take away 2, x equals negative 2. That's a 0. That's a value of x that if we plugged it into our expression, if I plugged it back in, negative 2 in for x, so that would be a negative 2 there, and then a positive 2. That whole thing would turn to 0, this first term, and then it would be 0 times, well, whatever's over here. That gives us 0 overall. Let's go on and solve the next one and see what our other 0 would be. I'm going to work this way. I want to get x by itself. Right now this plus 5 or this minus 5 is in the way, so to get rid of it I'm going to go plus 5, plus 5. Left side of the equation just stays 3x. The right side of the equation becomes 5. Now this 3 is in the way, it's being multiplied. I want to get rid of it. What I do to one side I have to do to the other side. So divide both sides by 3, gone. And that leaves me x equal to 5 over 3. And it's okay to leave this as a fraction. If you wanted to include it as a decimal, you could approximate it as 1.6 repeating. Yeah. Either way is fine. I kind of like to keep it as a fraction because it's more precise and it's nice and tidy. Just 5 over 3. That's a good answer. So those are our two zeros. They asked me to find the zeros. That's what we have to do. It's nice to have our expression split up into these linear factors with just x's in them, because then we get a set of equations. Here we had two equations that were very easy to solve to get our zeros. What we're going to see today is some examples where maybe our equations are not split up nicely into simple to solve equations, but we're going to be able to use our factoring tools to break those factors up, those bigger, uglier factors up into simple linear factors, and then we can write equations and solve them very easily. So that's where we're headed. All right, let's look at this first one. Example 1, find the zeros of the function with their multiplicities. And we haven't talked about multiplicities in this video yet. You should have seen your class. We'll describe them at the end of this problem. K of x is our polynomial. It's equal to all this. We're trying to find when or what values of x would make this whole thing equal to 0. And again, I see here I have things being multiplied together, a lot of things, in this polynomial. Like, first of all, I see this thing right here, this 3x plus 4 all to the 100th power. That means we're multiplying by 3x plus 4 by itself 100 times. Like, I won't even want to write them all out. That's all being multiplied by itself over and over and over again 100 times. Then that's being multiplied by, maybe this is my 100 of them there, the dot dot dots, the missing ones. And then it's also being multiplied by x minus 17 4 times. And 2 more times after that. So that one I did write them all out because I can write out 4 terms pretty easily. So just like in our example now, though, by splitting these up and kind of rewriting it all expanded, we can see that I have a bunch of linear terms, a whole bunch, like 104 of them, all being multiplied together, and they're equal to 0. And again, when we have things multiplied to get 0, any one of those things could be equal to 0. But all these blue terms, they're the same. So any one of these could be equal to 0. Let's write that equation. 3x plus 4 equals 0. That is a possible solution. If I went on to solve it, I need to subtract 4, 3x equals negative 4. And then divide by 3, x equals negative 4 over 3. That's a solution. And it actually happened how many times? So the multiplicity means like how many times did this solution come up when we factored out our equation? Well, we didn't write them all out here, but it's a solution to this one, to that one, and to all of those other 100 factors that came out when we split up this 3x plus 4 term. So 3x plus 4 is a solution, and it has multiplicity 100 because it happens 100 times in our factored form. Cool. So let's try and apply the same thing to the rest of the factors. All of these 4 factors are the same. They all are x minus 17. and any one of them could be equal to 0. So let's write that. That could be equal to 0. This will tell us what x's will make it 0. If I add 17, right now it's a minus, so I want to get rid of that. I want to add 17. X equals 17. So that's another solution. This one, though, will have how many times does it show up if we want to give its multiplicity? It showed up 1, 2, 3, 4 times. Or it was just 4 times. So multiplicity 4. So what we've done is we've taken our polynomial and we've looked at trying to split it up into linear factors, or other factors that would be really easy to solve as equations. And we did that here. It was pretty easy. We just had to expand our terms. When we had our exponents, we just expanded them. And we found out that if x was equal to 17, that would make our entire function equal to 0, because x would go into one of these factors of 17. Maybe it goes in right here. It would give us 17 minus 17. That's 0. And our whole function would be 0. So that's why x equals 17 was a 0. And it happened 4 times in our total factor. That's why it has multiplicity 4. Same thing with x equals negative 4 over 3. If we plugged x equals negative 4 over 3 into any of these terms, like over here, say I plugged it in there, we would multiply it out. We'd get, this would turn into negative 4 plus 4. That's just 0. We would get 0, and that 0 would multiply to make the rest of this polynomial 0. So that's why x equals negative 4 over 3 is a 0, and it happened 100 times when we split it up into linear factors. So that's an overview of kind of what we're doing here. Here we didn't actually have to use any of our factoring tools. We just had to understand that multiplying or raising something to the 100th power means it's being multiplied 100 times, or to the 4th power just being multiplied 4 times. In this next one, we're going to see what it's going to look like when we have some additional factoring to do first. So as this one is, we see, well, it's not exactly split up into the linear terms that we like, right? This equation, x squared minus 9, it's not a simple linear equation like, for example, our x minus 17 was. X minus 17 is really easy to solve. We just had to add 17. We didn't have any exponents on the x. Over here, we have a squared. So it would be nice if we could split this up into a bunch of linear factors so that they would be individually much easier to solve. So when I'm looking to factor something, right, we're like, we want to split this up. I'm like, well, we have factoring tools that we've discovered throughout this unit. So we have difference of squares, difference of cubes, sum of cubes, diamond box method. To me, looking at this one, I see that this looks like a difference of squares. I see a squared and another perfect square and 9. So I know that's going to split up into, let's see, a minus b, a plus b. A minus b, a plus b. So this first term, a is going to be x here. B is going to be 3. And then that helps me split that up. So by applying one of our factoring tools, I was able to take this thing that we didn't want to solve and split it up into nice linear factors. These would be very easy equations to solve. They're just one-step equations. We'll come back to those in a second. The next one says x to the 4th. Well, I don't have a tool that's specifically for x to the 4ths. But if we remember, sometimes we could use difference of squares when we had an even power. So this has x to the 4th. That's an even number. We might be able to split this up using difference of squares. So I'm going to make it look like a squared minus b squared. If that's the case, then a squared is equal to x to the 4th. It's saying what times itself would give us x to the 4th. Oh, well, x squared times x squared would give us x to the 4th. So a is going to be x squared in this case. X squared, and then b squared is equal to 16. No, yes, b squared is equal to 16, which means what times itself would give us 16? Well, then b is just going to be 4. minus 4 plus 4. So again, we should have seen this. If this looks confusing, go back to your factoring, the video on factoring differences of squares and cubes. But by applying difference of squares twice here, it's gotten us a little bit closer. We now have these two terms over here that are linear, and they're ready to find their zeros. And over here, we've gotten closer. We went from an x to the fourth polynomial, and we split it into two x squared polynomials. What I want to do next, before we go and find our zeros, I want to break up this any more if we can. And it looks to me like we can, because I see here another difference of squares, right? I see an a squared minus a b squared with x squared minus 4, because 4 is a perfect square. So let's rewrite this one more time. X minus 3, x plus 3. This is going to split up into two more terms. And then this one over here, this x squared plus 4, I don't see a way to split this up because, one, we don't have a formula for a sum of squares, and the one we do have for sum of cubes, sometimes maybe we could apply that if our power were a factor of 3, like if it were to the 6th or something, but because 3 doesn't go into 2, we can't split that one up anymore. So I think they were kind of stuck there with that term. But let's keep going on these. We still have our x minus 3, our x plus 3, and this one, I'm going to do it quickly. It's x minus 2, x plus 2. All right. But now we've gotten a lot closer, and we've split all of these. We've split it down into 4 linear terms, and then this one quadratic term that we can't quite split up anymore. So let's find the ones we can. First of all, from this one, x minus 3 equals 0. If I solve that, that's just going to be x equals 3. So that's one of our solutions. Let's do it again here. X plus 3 equals 0. X equals negative 3. That's a second solution. X minus 2 equals 0. So x plus 2, that's going to be a solution. And then x plus 2 equals 0. X minus 2. Ooh, I always do that. X equals plus 2. X equals minus 2. Those would be our solutions. So this gave us 4 zeros, 4 real solutions, 4 values of x that if we plug them in would make our expression 0. And we're left with this last term here that we can't really do anything with. Let's think about this though. Are there any values of x that we could plug in here to make this thing equal 0? Well, we know whatever it is, we're going to add 4 to it. And then, so it would be nice if this first term were negative. It would have to be negative 4. So another way to think of this is like x squared would have to be equal to negative 4 to make this happen. But I can't think of any numbers that I can square. A number times itself, like 2 times 2 would give me positive 4, but it needs to be negative. Maybe negative 2 times negative 2. Nope, that's also positive 4. So there are no real solutions when we get a situation like this. We can't split it up anymore, and we realize in addition that there are no numbers of x, no real numbers of x that we can plug in to get to 0. Later on in the year, we'll talk about how there are imaginary solutions to that equation, but not right now. So we found 4 zeros here, and multiplicity, none of these repeated. We had a positive 3, a negative 3, a positive 2, a negative 2. They all have multiplicity of 1. That would kind of be our solution to this equation. So we found 4 solutions, 4 real solutions to this equation, all with multiplicity 1, and we did it by applying our difference of squares a couple times to help split up into nice linear terms. Okay, what you should do at this point is go down here to example 3 and 4 and pause the video and try out these two And then when you're ready, or when you're stuck, or when you're confused, or after you've thought through it, come back and just watch me go through them really quickly so that you can clarify any mistakes. So again, pause the video now, try out 3 and 4, and then restart the video and watch me walk through them. When I walk through, I'm going to go through kind of quickly, so I'm counting on that you tried them out and have some stuff written down as we go. All right, so hopefully you've tried these out. Here in example 3, I want to split this up into linear terms as much as possible. I'm going to write it out fully. This is x minus 4 to the third, which means it's x minus 4 times itself 3 times. And then to me, this one looks like, oh, I have a cube term and it's being subtracted by another perfect cube. Here a would be x, b would be, cube root of 27 is 3 times 3 times 3 would give me 27. And then that splits up into 2 terms. A minus b, which is x minus 3, and a squared, which is x squared, plus bx, which is 3x plus 9. Okay, so this problem actually only asks us to find 2 zeros. As I'm looking at this, I see we're going to get a 0 from this one, x minus 4 equals 0, or x is equal to 4. That is 1 0, and it has multiplicity 1, 2, 3 times. It happened 3 times, so x minus 4 multiplicity 3. I also see another one I'm able to get here is x minus 3 equal to 0, or x equals 3. That's another value of x that would make this all equal to 0, and it has multiplicity 1. And then there are no real solutions that I can think of for this one. Again, if I tried to factor this with my diamond box method, 9x squared 3x, I'm like, I need factors that multiply to make 9 and add to make 3. And there aren't going to be any real ones that do that because, well, 3 and 3, they're going to add to 6. So yeah, that one's not going to work. No real solutions here. No reals from that one. So, but we did end up with the 2, just like the question wanted. X equals 3 is a solution. X equals 4 is another solution, and we found their multiplicities. Cool. So let's try out number 4, last one. This one does have a quadratic in it. So let's factor that one first. Again, diamond box method is my preferred method. It doesn't have to be yours. If you like the columns, that's fine too. 6x squared, 5x on bottom. So I need factors of 6 that add up to 5, 2 and 3. 2 times 3 gives me 6, yep. And 2 plus 3 adds up to 5. So then in my box, x squared, 6, 2x, 3x. Then I like to fill in this top one first. I know x times x gives me x squared. And then I would need a 2 there to make that one true, and a 3 down here to make those true. Cool. So that gives me x plus 2, x plus 3. And again, if that factoring that quadratic with all the terms feels tricky, go back and watch the video to refresh yourself on it, or pause and try it out on your own. Okay. So got that one factored. This next one is just, it times itself twice, x plus 2. And then this last one, I see that's a difference of squares. A squared minus b squared. A is x is equal to x, and b is equal to 3. So then that's going to give me x plus 3, x minus 3. So this is why it was nice to factor it all the way out first. I actually find that I get some repeats in here, right? I have x plus 2, x plus 2, x plus 2. That shows up 3 times. So for that one, x plus 2 equal to 0, x equals negative 2. That's one solution, and it has multiplicity 1, 2, 3. Because it showed up 3 separate times. I also see I got an x plus 3 that showed up a couple times. X plus 3 equals 0. X equals negative 3. That has multiplicity 2 because it showed up twice. And then our last one, I'm not even going to solve this equation. I just see that it's going to be right there. X equals positive 3. A positive 3 minus 3. And it has multiplicity 1. Oops. Multiplicity 1. And I'm abbreviating multiplicity. If it asked you to write it out, you could always just write it out. Okay. So that's kind of our summary. So to wrap this up, we're basically saying we really need to break our polynomial down into linear, I call them linear factors, basically factors of just x, not x squared, not x cubed, into x factors. And then we found our zeros and counted for multiplicity. And the way we broke them down, the way we break our polynomial down is by factoring. We had a bunch of different methods. We had to choose ones that made sense for our problem, but once we chose them, we just applied them, and we got a bunch of linear factors. We found our zeros. So like solving that x plus whatever equals 0 equation, figure out what x is equal to, that would be a 0. X equals, that's a 0 something, and then counted how many overall. All right, so once you've gone through these notes, tried these out, on the back side there's 1, 2, 3, 4, 5, 6 questions that ask you to do this. Some are pretty straightforward. Others may ask you to factor a quadratic. Some have differences of squares and cubes. A bunch of variety here just to practice that. So follow those steps, and I will see you next time.